The talk is how long is a packet, which could be interesting. Who am I? I haven't done a slide on that. My name is Stephen Donnelly. I'm the CTO at Endace. We're one of the sponsors. We're a packet capture company. If you want to find out about what we do, we have a table in the Europa room where we had breakfast this morning and where the lunches and things are. So you can go and talk to us there. We're also a SharkFest sponsor. So we are sponsoring a number of things, including the Group Packet Challenge, which Sake is organizing. That's where on Thursday night you get together in teams and you work on solving an escape room challenge. And if you want to do that, it's really good if at least one person on each team needs to come visit our table and get the instruction sheets, and it'll show you how to log into an Endace probe and download some packet traces that you can use to solve the first challenge, the first part of the packet challenge. And if you do that, it'll save you time. And if you don't do that, they'll give you the trace files when you go to the packet challenge on Thursday, but you'll run out of time to complete everything. That's what happened in Berkeley, so it's worth having a go. All right, so this talk is how long is a packet? So, it's a good question, isn't it? How long is a packet? When you think about how long a packet actually is physically, it's to do with the serialization time. So how long does it take to send a packet on a medium? Right, and we can get a formula for that. It's pretty straightforward. So length is the size of the packet in bits divided by the bit rate times the velocity. If you look at the first part of that, bits divided by bits per second, the bits cancel out, you're left with seconds. So that's just how long does it take to send a packet at a particular line rate. And then velocity is the speed of the signal within the media. And the seconds, again, cancel out, you're left with meters. So if we imagine just sending, start off and make it simple, if we send 1 bit on a 1 gigabit per second network, divide that by 1 billion bits per second, and multiply it by the velocity. So what's the speed? How fast does a signal actually travel in, say, a fiber network? So the speed of light in air is about 3 times 10 to the 8 meters per second. In glass fiber, it has a higher refractive index, so the light travels more slowly. It travels at about 2/3 the speed of light, which is very convenient because it makes it about 2 times 10 to the 8 meters per second. So what that means is 1 bit on a 1 gigabit per second, say Ethernet link, in fiber is about 20 centimeters long. So about that long. Now fortunately we're not in the US, so I don't have to convert it to imperial, but if you did, it would be about 8 inches. And if we look at our picture back here, our tape measure is at about 8 inches. So that's about how long 1 bit is at 1 gigabit. Okay, so if you think of a bit being 20 centimeters long, how long would a 100 byte packet be, for an example? So 100 bytes times 8 bits, work it out, it's about 160 meters long, or 525 feet if we're in America. So if your piece of fiber connecting 2 devices is over 160 meters long, when you think about it, that means that when you're sending that 100 byte packet, there's a certain point in time where the packet only exists in the fiber. It's been finished being sent by the sender, it hasn't started being received yet. It just exists as a pattern of light inside the fiber. So if it's a UDP, that's the only place that packet exists, right? You send it and you forget it. If it was a TCP packet, then the sender is going to hold a copy of that packet in its transmit buffer because it might have to resend it. So the packet exists in 2 places in that case. Okay, so what happens if you have a longer piece of fiber, right? So let's imagine, for example, that someone conveniently dug a piece of fiber for us from Berkeley, which is where the previous SharkFest was, which is near San Francisco, to here, Estoril, it's close to Lisbon. Those are the nearest airports I could find. There's this great website, great circle maps, and it tells us that the distance between them is 9,142 kilometers. So you can imagine if we started sending data into a piece of fiber between those 2 sites, and it was a straight line and there were no switches or routers, just imagine that we had a strong enough signal to send that. How much data would you be able to put into that link before it starts coming out at the other end? And again, we can use the same formula, just rearrange it slightly. So the amount of data that you can put in is the length of the fiber in meters, so 9 million meters, divided by the speed of light, times our bandwidth, which is a gigabit, and it's about 45 megabits, or about 5.7 megabytes. So you can think of that piece of fiber as a storage medium, where I can write up to 6 megabytes of data into it before any data comes out. Now, a USB stick can store gigabytes, and it's much smaller, so it's not a very practical storage medium, but it does actually have a storage component, if you like to think of it that way. It's also worth pointing out, if you look at the first part of it, the delay over that piece of fiber is about 46 milliseconds. So that's proportional to the amount of storage that we're putting in there. And we refer to this as a bandwidth delay product. So it's the bandwidth of the link, which is a gigabit, multiplied by the delay, so that 42 milliseconds times a gigabit. Why does that actually matter? Well, if you think about UDP, you just put packets in there and forget about them. So you could just send a gigabit per second, fire packets in there, they'll come out the other end eventually, there's no problem. There's no feedback, there's no flow control, unless you implement it at the application layer. And there are protocols that do that, so Quick from Google, Quick UDP internet connections. If you're connecting to Gmail from a Chrome browser, for example, to G Suite, it's probably using Quick, not TCP, so you need to be aware of that if you're trying to capture those packets. There are quick dissectors in Wireshark, so it can decode that stuff, and it will implement flow control and all of those things at a higher level on top of UDP. But most of the time we're talking about TCP. And with TCP, you send data and you wait for an acknowledgement. How much data can you send before you have to stop and wait for an acknowledgement is the receive window. So the receiver says to the sender how much data it's allowed to send before the sender has to stop and wait for an acknowledgement. The sender has to have enough buffering to hold all of the data in that window. And if the window is too small, the transfer is inefficient, right? You imagine that link which has 6 megabytes of data in it. If my window is only 2 megabytes, I send 2 megabytes into the link, I have to stop sending for 2/3 of the time before I can get an acknowledgement back and then start sending again. So I need my receive window to be larger than that. But the problem is the sender doesn't influence the receive window. The receiver sets that. The sender has no way of saying, hey, I need to be able to send more data than that. Doesn't work that way. So the TCP window, and this is one of these things that comes up in SharkFest talks quite a bit, where people are talking about performance analysis and trying to understand issues to do with networks being slow. Your TCP window, you really want it to be about twice the bandwidth delay product. So that's enough time for the packets that I'm sending to get to the far end, and then for the acknowledgements for those bytes to come back to me so that I can send packets continuously, right? So I want to just keep that train going all the time, just keep sending packets, fill up 2 times the bandwidth delay product. So for our 9,000 kilometer link with our gigabit connection, if we want to have a single TCP session and we want to keep it full, we want to be 2 times, rounded up, 6 megabytes. So that's 12 megabytes in size. No problem. The next problem is the TCP window field in the TCP header is only 16 bits. So it can only represent 64 bytes. When you negotiate a TCP session, though, and you can negotiate a window scaling parameter. So you can advertise a window scaling parameter and say, okay, I want to use this window size field, but I'm going to scale it up. The largest scaling factor you can have is 14, so 2 to the 14, which means the largest window size that a receiver can advertise is 1 gigabyte. Now we only need 12 megabytes, so we can say 2 to the 16 times 2 to the 8, 16 megabytes. There's no problem. So as long as the receiver is advertising window scaling of that size, then you can negotiate that size, no problem. So you might be thinking at this point, but Stephen, last time I went to a website in California from here, I didn't edit the configuration of my TCP stack. I didn't change my operating system. So was I doing something wrong? And the answer is no, for a couple of reasons. One of them is you probably weren't expecting to get 1 gigabit per second over a single TCP connection from California from here. There's usually going to be some bottlenecks in between, and you're not going to expect to get that much performance. The second reason is a thing called TCP Auto Tuning. So in the good old days with VAXs and so on, if you were running TCP, you'd have to go and edit the TCP window size manually. But modern operating systems have an auto-tuning capability where the idea is my operating system is going to open dozens or hundreds of TCP connections simultaneously. I don't want to allocate 16 megabytes to every one because that would chew up a whole lot of memory in the machine. I want to start with a fairly small window, and then if I discover that a particular TCP connection has a high bandwidth delay product, then the operating system will just allocate more memory to that buffer and advertise a larger window. The problem with that is that the window scale is set at the beginning of the TCP session. So there's a limit to which you can adjust the window. Not all devices on the internet do run modern operating systems that support window scaling. Modern versions of Windows will auto scale up to about 16 megabytes. So they would actually work fine on this connection that we were talking about, our example. Linux, I believe, will auto scale to 4 megabytes by default if you're not otherwise changing the configuration. But it is very specific to kernel versions. It has changed a lot over time. And it is also may depend on your distribution. So different distributions set different parameters. So you may find that if you are trying to do high bandwidth single TCP connections over high bandwidth delay products, then you have to go and read a bunch of TCP tuning guides, and there's quite a lot of them on the internet. So people like ESNet publish those kinds of things. So is auto-tuning sufficient to solve this problem? We just don't need to worry about it anymore. Well, maybe. As we said, not everything runs modern OSs. On the other hand, if it's an Internet of Things device, it's a small embedded device, you may not be able to change its configuration, right? So your Alexa may not need to get a gigabit from California to here, but you probably can't say, Alexa, set the window size to 16 megabytes. If you're running TCP over a link with a very high bandwidth delay product, auto-tuning may not do it. You may need to tune it. So an example of that would be either a very high bandwidth link, like 100 gigabits, or a very long link. So what's an example of a really long link? This is going to work. There we go. So you may have seen this diagram. It's quite a cool one. It's from a JPL scientist, and it's a 2-scale picture of the Earth and the Moon. So the Earth and the Moon are size to scale, and the distance between them are to scale. And the bouncing dot represents how long it takes a signal traveling at the speed of light in a vacuum to travel between the Earth and the Moon. It's about 1.25 to 1.26 seconds each way. So what would the bandwidth delay product to the Moon be if we were trying to do a TCP connection to the Moon? One advantage is because it's traveling through a vacuum, we can use 3 times 10 to the 8 meters per second rather than 2, so we don't have to have fiber. Whoops. But what bandwidth would we use? So it turns out this has actually been tried. NASA had a satellite called Lady in 2013 with an optical laser communications terminal on it, which was able to send data from the Moon to the Earth at 622 megabits. I don't know why it was 622 megabits specifically, but that was the rate that they had. And if you work that out with the formula that we had, you can see that the bandwidth delay product is about 99.6 megabytes. So you're at the Moon, you're sending at 600 megabits, you can send 99 megabytes of data before any of it arrives at Earth. So to set up your TCP window, if you're using TCP, you'd need to set it to 200 megabytes. That does fit within our 1 gigabyte limit, so that would work fine in theory. But it is a very high delay, so your slow start would be very, very painful. TCP might not be the best option for that. If you think about it the other way, what if we just set our window to 1 gigabyte, the maximum amount, then how much bandwidth could we get from the Moon? What's the highest throughput we would get? It turns out it's about 3 gigabits per second. You might be concerned about that. You might think, hey, I might want more data. I might want more bandwidth from the Moon than 3 gigabits. Is this a limited TCP? Well, look, that's per TCP session, right? So if you need more bandwidth from the moon, just open multiple TCP connections, parallel FTP, that kind of thing. If you think even further away, somewhere like Mars, Mars is 56 to 400 million kilometers away. That's between 3 and 23 minutes for light to travel between Earth and Mars. So that's something where TCP session setup is really not going to work. So you wouldn't use TCP on that. There is an interplanetary network proposal, and there's a suite of protocols called disruption-tolerant networking, which can be used for that. And it's more of a store and forward thing, where you just send a whole bunch of data with forward error correction and collect it at the other side. All right, so let's come back to Earth a little bit. We were talking about how long is a packet. Start from something simpler. How long is an Ethernet frame, right? Everybody knows an Ethernet frame is like 64 to 1500 and something bytes. So here's a typical diagram that you would get. You've got your MAC header at the start, you've got a link length, there's some Ethernet payload, and you've got a checksum at the end, 64 to 1500 bytes. That's fine, but how long is the Ethernet packet actually on the wire? It's slightly longer. Right, so at the beginning of the TCP packet, you've got some preamble and you've got a starter frame delimiter, and then at the end of the packet, there's this interframe gap, which is a guard time between packets. And this all goes back to when Ethernet was collision-based, but it's still carried over into modern Ethernet, so it's still there. So actually, an Ethernet frame on the wire is between 84 and 1538 bytes. Okay, you know, it's a small difference. It's pretty easy to understand that. That kind of makes sense. And that's been around for quite a long time, and the only number you have to remember there really is 20. So you're just adding 20 bytes to go from the conventional Ethernet frame length to the frame length on the wire. But then some smart people said, well, Ethernets are great. What we'd really like to do is run multiple separate Ethernets over the same Ethernet. So we'll come up with a VLAN header. But we still want to be able to send our 1500 byte Ethernet payloads over this. So what we'll have to do is we'll make the Ethernet frame a bit longer. Okay, so we'll just extend it by 4 bytes. Okay, now we're at 64 to 1522 or 84 to 1542. You know, it's just small change. It doesn't matter too much. We just make it a little bit longer. And this was fine until some other very smart people said, well, these virtual Ethernets are fantastic. We really like them, our customers are using them, but we want to use them as well in our carrier network. So we want to send VLANs over VLANs. And the guys at the IEEE were getting a bit frustrated at this point, and they said, you guys are nuts. You keep adding more bytes to these Ethernet frames. What we're going to do is instead, we're going to invent an envelope frame. So the envelope frame basically says you can have anywhere between 4 and 482 bytes of overhead between the MAC header and the Ethernet payload. And you can put in as many VLAN tags as you like. You can do tunneling, you can do whatever crazy stuff you want to put in there. You can put in MAC security, whatever you like, as long as it fits into that space. We're not going to keep changing the size of the Ethernet frame, right? So what IEEE says is that the maximum length of an Ethernet frame is 2000 bytes. Or if you're looking on the wire, you're adding 20, so it's 2020. So everybody knew that, right? Everybody knows that the very common knowledge, the maximum size of an Ethernet frame is 2000 bytes. Yep, nobody's objecting, so everybody knew that. But hang on, you might be saying, I'm sure I've heard of packets bigger than 2000 bytes, right? What about jumbo packets? Well, the thing about jumbo packets is they're not IEEE 802.3 compliant. So a bunch of vendors said, hey, we want bigger packets than that, let's just make bigger packets. You can do that, but it does cause a few problems. One of the problems is that in Ethernet, there's no way for an Ethernet switch to signal that a packet is too long to be sent over a particular link. All you can do is drop it. There's no fragmentation. And we'll come back to fragmentation a little bit later. The second reason that IEEE didn't like, IEEE wants Ethernet to be interoperable. If it's Ethernet, it should always work. If you start introducing invalidly long packets, then it suddenly breaks, and there's no way to tell what's happened. The second problem is FCS weakness. So in order to determine when an Ethernet packet arrives, if it has a bit error in it, there's a checksum at the end, right? This frame check sequence at the end that we saw. Problem is it's only 32 bits long. As you make the packet longer and longer, that 32-bit checksum stays the same length. So you're essentially using a certain number of bits to protect over a longer and a longer payload. What will happen is, as your packets get longer and longer, the probability that a bit error could occur in the packet and produce the same checksum gets higher and higher. And once packets are over 2,000 bytes, the probability of this happening becomes once or twice a day. So you could receive an Ethernet frame, you look at the checksum's correct, but there's actually an error in it. It's been modified on the wire. And that could be catastrophic, right? There could be a safety protocol, or it could be financial trading or whatever. Now the good news is most protocols on top of Ethernet have another layer of checksums. So TCP has its own checksum. The probability of you getting a bit error that has a collision and produces a correct Ethernet checksum and produces a correct TCP checksum is pretty low. So you're probably safe. But from the Ethernet standards point of view, they see that as worryingly dangerous. So that's one reason that people don't like using very long Ethernet frames. Also, if you are using large packets with NFS or iSCSI or something like that, they tend to have their own stronger checksums that are used over that to protect against that problem. Okay. So this is SharkFest. We should be talking about Wireshark. How does Wireshark report packet length? So this is where we get to the inevitable Wireshark demo. So bear with me, and let's see whether we can get a Wireshark demo going. Now, unfortunately for me, those screens are a really long way away, so I can't actually point to them very easily, but what I'll do is I'll make this a bit bigger, and I'll just point with the mouse a little bit. Okay. So here is Wireshark. We can click on a packet, move this over a little bit. And when we're looking at the size of the packet, it's one of the first things it tells us. It's right on the top of the screen. Frame 1, 60 bytes on the wire, 480 bits. It says 60 bytes were captured of that packet, all 480 bits. Ethernet 2 frame, and it's IP packet, UDP, fine. That sounds okay, and if we open this up a little bit, it tells us that it's Ethernet. There's a couple of different numbers in here. There's the frame length, which is 60 bytes. There's the capture length, which is also 60 bytes. But when it says 60 bytes, exactly what is it referring to? So that, didn't we just say that the minimum packet length was 64? So what's happening here is, if we scroll down a little bit, we see it's an Ethernet frame. We can open that up. We can see it's IP. There's some trailer in here, but there's no checksum on the end of the packet, right? So this particular capture system has not captured the frame check sequence at the end of the packet. And this is quite common for most network adapters. A network adapter, when a packet arrives, it checks the checksum. If it's a bad checksum, it drops the packet, it doesn't give it to the OS, and it counts it. If the packet does pass, then it strips the checksum off, because the operating system doesn't need to know. Right? All we need to know is that the Ethernet frame was valid. So when Wireshark said at the top here, it said in big bold letters, bytes on the wire 60, it actually meant 64. Okay, not a big problem. We just need to be aware of that when we're dealing with packets on the wire. One of the nice things about Wireshark is if you click on one of the packet headers, you can sort by it. So I can click on length here, and I can see here's the shortest packet, it's 54 bytes, largest packet is 62. So hang on. And I need to scroll up to the top again because it doesn't resort. So there's 1514 is the longest packet, and if I sort for length, and I scroll back up to the top again, the smallest packet is 42 bytes. Okay, well that's a bit confusing. So now we're not at 60 bytes, we're at 42 bytes. And Wireshark quite happily tells us this packet was 42 bytes on the wire, 336 bits long. And we know it can't have been, because we know Ethernet is supposed to be 64 bytes. So if we look at what type of packet this is, it's an Ethernet frame, and it's an ARP frame. So ARP is not IP, right? ARP is one of these protocols that sits alongside IP. And it's used for saying, hey, I've got an IP address, I need to know what MAC address to send it to. The contents of that is pretty small. So if we look at the ARP request, we can see, I'll scroll this over so you can see the hex dump. it uses less than 64 bytes. So what the Ethernet sender will do when we're sending that frame is it'll pad it out to 64 bytes and it'll put the checksum on the end. So the frame on the wire was 64 bytes, but Wireshark is telling us that it was 42. It just hasn't captured that stuff. Is it a big problem? Maybe. If you were running two devices on the same Ethernet and you wanted to communicate information between them, maybe you could put some bytes into that padding and you could communicate in such a way that this packet capture wouldn't see it. Is this Wireshark's fault? No, not really. When Wireshark reports these two numbers, this frame length here and this capture length, what it's doing is it's getting those two numbers from libpcap. So it's capturing using libpcap from, or winpcap or npcap from the operating system. So the operating system says to libpcap, this packet is 42 bytes long. The operating system is getting it from the device driver for the network adapter. The device driver for the network adapter is probably getting it from the hardware. So somewhere within that stack, it's looking at the frame and saying, well, there's only 42 bytes of data here. I won't bother giving you all that padding because it's just zeros, right? There's nothing interesting there. So Wireshark is simply reporting the information that it got from the capture stack. So not really Wireshark's fault, it's just the way that it works. You just need to be aware of that. So if you're seeing these short frames and you're thinking, oh, is there some error on the link? No, it's fine. Okay, so see what else we've got. So here is a packet capture. Here's another one. So we're starting with an ARP packet this time. Scroll this up a bit, zoom this up. So the first packet in this link is an ARP packet again, but this time it's 64 bytes reported length. So what's changed here? So I'll move this out of the way a little bit. If we look at the Ethernet frame, we can see that it's an ARP packet. We can see the ARP request here is taking up most of the packet. And then there's a whole bunch of zeros, and then there's a checksum. So Wireshark is now telling us this frame was 64 bytes on the wire. Here is the trailer. That's that sequence of zeros that the sender was using to pad the frame out to make it long enough. And then there's the check sequence at the end, and it can even tell us that the checksum was correct. So this is the same type of network traffic, but captured on an adapter where it does capture all of the frame length, including the Ethernet checksum. And if we look, again, we can sort by length. And scroll to the top. And yes, there isn't anything in here that's smaller than 64 bytes. And if we sort for the longest packet, make it slightly bigger, there's only 600 bytes. There weren't actually any 1500 byte packets in here, but they would have been reported as 1522 or so. Okay, so that all sounds fine. It's just a different capture system underneath where it's a different network adapter or it's a different driver, and it is giving you that checksum length. Most of the time, Wireshark and the PCAP will detect automatically whether or not the capture system is recording the checksum, and if it's present, it'll list it here. Sometimes you'll receive a PCAP file from somebody and it isn't marked up correctly, the link type is not set properly, and it won't know whether or not there is a checksum there. So the way you can have a quick look is you right-click, you go into the protocol preferences, and then there's a setting in here for assume packets have FCS. I know that's a bit small, that's what the option's called. So if you turn that on, it will force Wireshark to take the last 4 bytes of the frame to be an Ethernet checksum. If I turn that on in this trace, it makes no difference because it does have a checksum. It already guessed that correctly, and there's no problem. If you have a trace that has checksums and hasn't been picked up properly, then it'll report it as a unknown Ethernet trailer. So if you get an info message about an Ethernet trailer, just have a look. It might just be that you've captured the checksum. You just turn that setting on. It is worth noting, though, that if you turn that setting on, and we go back and we open our first trace file, which didn't have an FCS, all of a sudden, it's full of errors. Right? This is the same file that we looked at first, but now we're getting all kinds of crazy errors all over the place. Ethernet frame check sequence incorrect, segment not captured, all of these weird problems. And the reason is, we can see this Ethernet line is red. We can open that up. frame check sequence is incorrect. What it's doing is it's assuming that the last 4 bytes of the frame is the checksum, because we told it to, right? We just set that protocol preference. So again, if you're opening an Ethernet file and you're getting just massive amounts of errors all over the place, and you're getting errors about checksums being incorrect, it may be that the trace file doesn't have checksums in it. You just need to go to the protocol preferences, turn off, make sure that assumed packets have FCS is turned off, and all of a sudden the trace is fine again. So that will trip you up occasionally. Okay, what else can we see? Okay, here's another one. Here's another trace file. Just make sure we can see the length column here. Okay, oh, that's interesting. So we look at this trace file, it's sorted by time, and we've got some packets here which are 2,900 bytes long. Well, that's a bit surprising, right? Okay, maybe it's a jumbo packet. How big do they get in this trace file? So let's sort by length. We'll sort by biggest first. I'll scroll back up to the top. This is really big. 23,234 bytes. So somehow I've ended up with a packet that's almost 24 kilobytes in size in my trace file. It seems a bit odd. What's going on? Well, look at the Ethernet length. Wireshark is telling us that it was 23,000 bytes on the wire. It's an Ethernet frame, it's IPv4. What does IPv4 say? Well, IPv4 agrees. IP header says this is a 23,220 byte packet. So what was going on? This is an example of capturing packets on the machine that was sending the packets, okay? So this trace file was captured on the machine that was sending this particular packet. It was a transmitted packet. And what's happened is the network adapter has some offloads enabled. So it has transmit segmentation offload turned on. And what that means is the operating system, when it wants to send, say, 23 kilobytes of data, it can just send 23 kilobytes in a single IPv4 packet to the Ethernet card. The Ethernet driver or the Ethernet hardware will then segment that down into smaller 1,500 byte packets and send them individually and deal with all of the ACKs. But because the PCAP is capturing that sent packet at the operating system level, not actually at the wire, it's seeing this much larger frame. So if you do see these enormously large frames, it's probably because you've captured on the machine that was sending the packets or receiving the packets, and it has one of these offloads enabled. Now some people will say, well, what you can do is just disable the offloads, right? So you just turn the offloads off, this will go away, you'll start seeing the 1,500 byte packets, that's okay. The problem with doing that is the reason those offloads are there is to reduce the packet rate on the machine, right? And the reason we want to do that is to reduce the amount of CPU time we're spending sending and receiving packets. It's an efficiency thing. So if you have a production server and you turn off these offloads, you're going to increase the CPU load on the machine, you're going to increase the interrupt load on the machine, you're going to change the performance of the applications that you're trying to understand. So I would not recommend doing that. I think you're much better off capturing the packets from the network using a span port or using a packet tap or something like that, rather than doing the packet trace on the end machine. Okay. I've got one more. Let's have a look. Here. Okay, so here's the trace file. If we have a look at it, I'll zoom it up a little bit. Hopefully that's visible. Okay, so this is ICMP. It's just a ping packet. And what we've got down at the end here is there's IP, there's ICMP, and then there's Exablaze trailer. Okay, so what's happened here? This is a packet trace that's been captured from the output of a packet broker, right? So a packet broker is a device. There's lots of vendors here selling packet brokers. What they do is they capture packets on a number of different ports and then essentially span them to an analysis port or a mirror port, and they add a trailer on the end, which gives you a lot of really useful information on there. So it tells us, in this case, we look at the packet content. The highlighted part there is the entire trailer. It's got the original checksum for the packet before the trailer was added. Then it has a device ID, so which packet broker it is. It's got a port number, so which port on the packet broker was this packet captured from. And it has the timestamp. So that's the time that the packet arrived at the packet broker, not the time that the packet arrived at libpcap. And then after that is a pad byte, and then there's the checksum for the frame. Now there's nothing wrong with that. I don't want you to think that I'm saying that packet brokers are bad, but what I'm saying is, as far as Wireshark is concerned, this was a 118 byte packet because that's the size of the packet that libpcap got when it was looking at the frame that arrived, which already had the trailer on it. So if you want to know what was the size of this packet before the trailer was added, you have to do some maths. Right? So there's nothing wrong with packet brokers. They're a very useful thing to do, but you need to be aware when you're analyzing traces that these things are potentially there. You may want to strip them off. You can use some tools to remove the trailers, or you may just want to keep that in mind. So again, this 118 bytes on the wire, it's not really on the wire, or was it? It was on the wire as far as the libpcap was concerned, but it wasn't on the wire on the other side of the packet broker, which is maybe what you're interested in. So maybe Wireshark should have a setting to say, give me another column which was the packet length without the trailer on it. That might be a useful thing. Does it matter? So sometimes Wireshark gives us the wrong packet size, essentially. It's not really what the length was on the wire. Is that a problem? Okay, let's jump back into here. There's a few notes here, so if for some reason you're looking at the slides later, you don't have the trace files, we've just summarized what's on there. So that's about the capture length. This is about the NIC accelerations and how the point of it is to reduce the effective packet rate or to make it more efficient. And then pseudo headers. Now, I was talking about packet brokers in particular, but there are a few other places you can get pseudo headers or packet headers or trailers. They can either be on the beginning of the packet or on the end. Some link types, we heard a little bit about, one of the core developers was talking about USB capture. Now if you're looking at a USB trace capture in Wireshark, there's a pseudo header on the beginning, which is bytes to do with the addressing of USB that weren't actually on the Ethernet, or weren't actually on the USB in this case, link, but it's included in the wire length bytes, so you just need to be aware of that. Same for PPP. There's a PPP pseudo header that gets added. If you're capturing in Linux using SLL Linux, there's a pseudo header that gets added. And then obviously packet brokers, RSPAN and ERSPAN, they can all add different headers onto packets, making them appear longer than they really were. So is that important? Well, one place that comes up is when you start talking about speed and throughput. When you think about speed, we're generally talking about the amount of data transferred over a time period, right? So 1 gigabyte in an hour, that's a throughput. We typically normalize that to bits per second, so 1 gigabyte per hour is 2.2 megabits per second, right? It's the same thing, it's just bytes over time. Bandwidth really refers to the maximum throughput for a link, rather than what you're seeing second to second. And then goodput is the concept of how much data was successfully transferred. So if you have a TCP connection and there's retries occurring, then the goodput can be lower than the throughput. So the total amount of data successfully transferred is less than what was on the wire. So when you start trying to work out a throughput or a goodput from a packet trace, if that packet trace is not accurately telling you the packet length, then you might over or underestimate the throughput that you're getting on the link or the link utilization. If you think about it from the point of packets, smallest packet that we can have, as we said, on the wire is 84 bytes. So it's our 64 byte minimum length packet plus the preamble and the interframe gap. 100% link load, it's 1.5 million packets per second, roughly. If you looked at only the Ethernet part, 760 megabits. If you're looking at just the, say it was an IP packet, then the IPv4 payload is 500 megabits. Remember, the link is still running at 100% load. It's completely full, you can't put any more data through it. If it was a TCP packet, you're down to 300 megabits. And if you were looking at the TCP payload, so the contents of the TCP frame, you only get 6 bytes per packet. You're only going to get 71 megabits, even though that gigabit Ethernet link is fully loaded. So you've lost 93% of your link capacity. So this is why you shouldn't try and do bulk transfers with very small packets, obviously. Nobody would do that. 1500 byte packets makes a lot more sense. You're down to about 80,000 packets a second for 1 gig. Obviously at 10 gig, multiply it by 10. For 100 gig, you're going to be at 8 million packets per second. So on a 100 gigabit Ethernet link, you may still want to have your NIC offloads in order to reduce the packet rate, because 8 million packets per second is probably too high. So the efficiency for 1500 byte packets is 949 megabits. So you've lost about 5% of your link capacity to the Ethernet overhead or the protocol overheads. So if that's true, you've only lost 5%, why would you bother with jumbo packets, right? So if you can do the same calculation for jumbo packets, you'll gain 1 or 2% of extra throughput over that link. So the main purpose of jumbo packets is not to increase the link efficiency, it's about reducing the effective packet rate, just to reduce the load on the OS. Is it worth it for the interoperability hassle? That's a good question. Okay, so thinking about packet capture, you should always use the length, not the capture length. The capture length is, if I say I only want to capture the first 64 bytes, the first 128 bytes of the packet, if you do that, you'll underestimate the throughput, obviously. If your capture system doesn't capture the checksum and the padding for small frames, then you're going to underestimate the link bandwidth when you do that calculation. If your capture system has pseudo headers like PPP, or if you're using a packet broker, you're going to overestimate the bandwidth because your packet lengths are all slightly too long. And if you have NIC offloads, you're going to have two problems. First of all, the packet rate is actually going to be wrong. The packet count is going to be wrong. And you're also going to get the throughput underestimated. And if you're trying to compare, say, the statistics from your server to your switch port statistics, they're not going to line up because your server is only counting these large packets, whereas the switch is going to count the actual 1500 byte packets that it saw, and you're going to be saying, well, where's the discrepancy coming from? And if you're thinking about provisioning, it's often worth remembering that small packets have an oversized impact on the link utilization, right? So if you're sending lots of small packets, it's going to fill up the link pretty fast. Real networks are not all 1500 bytes or all small packets. It's going to be a mix. On average, most studies seem to indicate that the average packet size on the internet is getting smaller, and that's because of streaming stuff, streaming media, Netflix, voice over IP, gaming, financial feeds and so on. They all tend to use relatively small packets typically, and that is effectively reducing the efficiency of your links. Whereas your backups, that kind of thing, bulk transfer is going to use large MTU. All right, makes sense. Okay, so one of the things we mentioned earlier is Ethernet can't deal with a large packet trying to go onto a link with a small packet. And another way of talking about this from the IP point of view is MTU mismatches, right, which causes fragmentation. So here's a nice picture of fragmentation. These are all obviously stock photos. The attribution links are in the speaker notes if you want to find out where they came from. So what are we talking about here? So first of all, not all links have the same maximum packet size that you can send, right? Some of them may be Ethernet with jumbo enabled, some might not. Some might be PPP, you might have some encapsulation, you might have a VPN, for example. You may have some virtualizations, you may have some VXLAN or some Vinegar or whatever, and that's encapsulating your data packets inside other Ethernet packets, which makes them smaller. Now, when an Ethernet switch receives a packet that's too large to go out an output port, it just drops it, and it can't do anything about it. It has no mechanisms in there for it to, other than counting it, can't say anything about it. But an IP router can. So what happens when you're an IP router, a packet arrives, you want to switch it onto a link where the MTU on the output link is smaller than the MTU on the incoming link. So if it's IPv4, we have this concept of fragmentation. It goes back to the origins of IP, where packets can be fragmented anywhere in the network path. So if I'm talking to somebody at the back of the room, you guys are all routers, any one of these routers could have a link with a small MTU. The packet can get fragmented in the middle. As a sender, I don't know about it because it happens somewhere in the network. The receiver knows about it because he has to deal with the fragments arriving. So it's up to the receiver to reassemble the fragments, but it's fairly inefficient. So the router in the middle of the link, which has to deal with this, usually does it in a slow path. There are some implementations that do it in fast path, but a lot of routers will kick it out to the CPU. The CPU has to do the fragmentation. There are also consequential problems with that. So if I'm taking an IP packet and fragmenting it, if any of those fragments gets lost, then as a sender, I can't resend one fragment because I don't know about it. I can only resend the whole packet. So if a fragment gets lost, it doesn't get ACKed for that whole packet. As a sender, I then need to resend the same packet again. It's going to get fragmented again. The whole cycle can repeat. Another issue is that IP fragments after the first one, they don't have all the layer 4 information in them. They only have the layer 3 information. So they have the IP addressing information, but they don't have the port information. So if between the point where it's fragmented and the point where it gets delivered, there's, say, a load balancer or a firewall, it can't necessarily, unless it's careful, it can't associate that fragment with the original connection because it doesn't know the port numbers anymore. And that can cause issues as well. It might get dropped, it might get sent through a different path, it might be delayed, and that can affect performance. So fragmentation is generally considered not a fantastic thing. So IP thought of that, IETF thought of that, and they said, okay, well, let's have a don't fragment bit, which I can set on my packets. So when I send them, I'll just say, well, don't do the fragmentation thing because it's a bad idea. So what happens when that packet then gets to the router, which needs to fragment it? It sends an ICMP message back to the sender saying, the destination is unreachable, fragmentation is needed, but you set the don't fragment bit, so you need to do something about that. And if you're in Hansang's talk earlier on, one of the packets in one of his trace files had that set, so an ICMP destination unreachable, fragmentation needed. So it does really happen. What's supposed to happen is this thing called path MTU discovery. So when I get a message back saying, oh, that this packet was too big, I should reduce the size of the packet, try sending it again. And that should be fine. IPv6, we all need to think about IPv6 now because it's a big thing. Some quite large fraction of the traffic going to Google in the US now is v6, mostly because of cell phone networks. So a lot of mobile networks are v6 based, just because we're running out of address space. Now, IPv6 doesn't support fragmentation in the middle of the path. I can't send an IPv6 packet and then a router in the middle fragment it. We don't have a don't fragment bit in IPv6, but it's essentially always set. So you can't do mid-path fragmentation. So if the router in the middle receives a packet in v6 that's too big, it has to send an ICMP v6 packet too big message. Makes sense, it's the equivalent of the fragmentation needed and don't fragment set from v4, but it's a bit more explicit. So you see packet too big, it's very clear what that means. The endpoints are expected to do PMTU discovery again, so that I'm supposed to reduce the size of my packet and send it again. What if it's UDP, right? So if the protocol on top of ICMP v6 is UDP, I can't change the size of that message. It has to be whatever the size of the packet is. So IPv6 has a fragmentation extension header that the sender can put onto the packet. So I'm a sender, I want to send a, say, 2,000 byte UDP frame. I can create 2 IPv6 packets with fragment headers on them, send them through the network, they get to the other end, the receiver reassembles them and then delivers the 2,000 byte UDP frame to the application. The application doesn't know that it was 2 IP fragments on the network. But that only works end to end. Okay. All right, so does this work perfectly? Does this cause any problems? So here's an example of a connectivity problem that I had in the early days of the internet. I'm at home, I'm connecting to my bank, I'm browsing their website, it's all working perfectly fine, and then I decide to log into the secure internet banking, and it doesn't work. Who immediately knows what the problem is? Does anybody recognize what that is? There are some core developers who are not putting their hands up because they don't want to show off. So the first, PPPoE, yes, exactly. So these things are not all the same, right? So most of these links are Ethernet, but this one here is ADSL. So what's happening with ADSL? Why is that a problem? It's my shiny new ADSL connection. I've got a whole 8 megabits or something of internet connection bandwidth. It's fantastic. But the MTU is different, right? So my home PC talking to my router, it's Ethernet, 1500 byte MTU. ADSL is PPPoE over ATM, in fact. So the PPP header has to fit inside the Ethernet frame has to fit inside a PPP frame inside another Ethernet frame. And what that means is the MTU for the packets inside is slightly smaller. There's an 8-byte overhead, so I only have a 1492-byte MTU size. But we just learned about fragmentation, right? So this should be fine. If I'm on my PC and I want to send a lot of data to the bank, I'm going to send a 1500-byte frame because that's my MTU. It'll get to the router, and the router will then say, okay, my outgoing MTU is 1492, I need to fragment it. So what it'll do is it'll break it into a 1492-byte fragment and an 8-byte fragment. It'll send those through to the far end. It should work. And same for the bank. So if the bank wants to send me a 1500-byte packet, because again, the MTU on the packet, there's a laser pointer. The MTU on the bank's end is 1500, right? So it'll send a 1500-byte packet out. It'll travel all the way through the network until it gets to the ISP's router, which will say, oh, we need to fragment it. So we'll just create 2 fragments, we'll send them through. It should work fine. What if somebody is sending don't fragment? Okay, so if I set don't fragment on my packet, it'll get to the router will say, we need to fragment this. It'll respond back to me with an ICMP message. I'll change my packet size and we'll continue. It should work fine. Likewise, if the bank, for some reason, sets don't fragment, then the packets will come through here, it'll get to the ISP. The ISP will generate an ICMP, destination unreachable, fragmentation needed, and don't fragment set message, send it back, and the bank should then do PMTU discovery, and it should work. But it didn't work. So what's likely to be the problem? Yep. Blocking ICMP messages in the firewall. Yeah, when we look at this diagram, there's something on fire, right? The firewall is probably a bad thing. So what's happening is the bank is saying, let's block all ICMP, because ICMP is apparently bad. Somebody from security said ICMP is a bad thing, so let's block it all. But because they're blocking these ICMP messages coming back from the internet, it means I can't connect to my internet banking. They've broken the internet, right? So what's the solution to that? Don't block ICMP destination unreachable. That's the first thing. Also, don't block ICMP v6, packet too big, right? You also need that message. So if you're going to start blocking things, understand what you're blocking before you do that. Is there a way to get around that? Yes, there is another solution, right? So if we imagine that it's my router which is opening a connection to the bank, when it goes to set up its TCP connection, it's not going to send a 1500-byte packet. It's only going to send a 1492-byte packet because it already knows that this MTU is smaller. So if the router was trying to connect to my banking login, it would have worked fine if I'd done the connection from there. So how can we make use of that? The idea is MSS pinning. So when you open a TCP connection, the sender will say, this is the largest size packet that I'm going to accept, regardless. Don't send me any segments that are larger than this, it won't work. So when my computer opens a TCP connection, sends a TCP SYN out, it's going to calculate the MSS based on its 1500-byte MTU. It's too big, right? So we know that there's this bottleneck in between. So what MSS pinning is a setting on the router that says, when you see a SYN coming past, and you know it's going onto a link with a smaller MTU, reduce the MSS. So change the SYN packet that you're routing through and rewrite it, recalculate the checksums to make the MSS smaller. And when you do that, when it comes to this end, the bank will receive that smaller MSS and it won't generate a 1500-byte packet, it'll generate a 1492-byte packet, and then it'll work, even though they're blocking ICMP. You can do that in Linux, it's a good thing. but it's working around brokenness in the internet because somebody decided to block ICMP. Okay, so we're getting close to lunch. Quick recap. We talked a bit about physical packet lengths. We talked a bit about bandwidth delay product, or what the IETF likes to call long FAT networks, or LFNs. We talked a bit about Ethernet frame lengths and how it might not be what you think. It's not 15 mumble bytes. It's actually 2,000 bytes is a maximum. We talked a bit about Wireshark and the PCAP and how packet capture works using different types of adapters, and how Wireshark can sometimes be slightly misleading. It's not that Wireshark's lying to you, but it's reporting accurately what it was told by the capture system, and that might not always be the number that you want. So if you're looking at those I/O graphs and you're plotting bandwidth or throughput using the I/O graphs, it's using those cap length numbers, so it might not match exactly what you're seeing off your switches. We talked a bit about throughput calculation, how that's affected by packet size, and about fragmentation and PMTU. So as a reminder, please do fill in your survey on the app. As Hensang said in the previous session, if you're using the guidebook app, you can go to the session, you can fill it in, you can tell us how we can improve the session. It's always good to get feedback. I do encourage you to enter the group packet competition. So the event tonight is the treasure hunt, where you're going around talking to the different vendors. The event tomorrow is the individual packet challenge. So you can go and collect the individual packet challenge forms from reception. If you want to do the group packet challenge, ideally find a bunch of people who want to do that, get together, and at least one of you needs to go to the Inday stand and get the instructions for the group packet challenge part. Okay, so thanks.